So, hi, I want to welcome you all to the Data Science Initiative sponsored Red Talk this evening. We are delighted to welcome Dr. Matt Hansen. He is a professor in the Department of Geography at the University of Maryland, where he also got his PhD. I'll say there is a North Carolina connection because it looks like your master's degrees are both from the University of North Carolina at Charlotte. Yeah. And his research area is in land cover extent and change, looking at national, continental, and global scales. And so I'm going to leave the introduction short and let Matt talk a little more about sort of his background and the things that are relevant to what he'll be speaking about this evening. So thanks very much for being here. I will just mention that if you're a statistics student, the sign-up sheet is going around Catch Rebecca, because she's got it.
All right. Thank you very much, Allison. Thanks a lot for coming. Can you all hear me reasonably well? So I will be talking about our work. Our work is mainly using Earth observation data, satellite data, to track the changing Earth, principally how we are modifying the land surface. I'll go over some of our generic methods and some example products and dynamics. I guess I'd just start by saying that it's a cool, this forum is appropriate for it. I think the people who are good in our field are quantitative. They can program, they can do stats and math, they can understand algorithms. But they also have to have the domain expertise of the environment, environmental science, geography, human interactions with the environment, pattern recognition. So that it is kind of an interdisciplinary, multidisciplinary work, and the people who have all those competencies do really well. You don't have to have all of them. There's a lot of my students who might just be mainly geographers, and we keep the programming light for them, but there's other folks who are really quite deep in the programming, and they can contribute just as well. But really, if you have all these skills, you can do some serious damage. Our work is at scale. We try to map big areas because there's really no UN Food and Agriculture Organization or some other UN agencies are responsible for understanding what's happening in the world's forests officially, statistically, or agriculture. And they take data from all the countries who submit their estimates per their own national definitions, and you don't know really what's happening with the planet. And the idea behind the satellite is that the satellite's polar orbiting is taking the same engineered signal across all the geographies of the Earth, and if we run algorithms in an appropriate way, we can say, this is what's happening in Brazil's forest, this is what's happening in Congo's, this is what's happening in Indonesia, these are the trends, and we can kind of get an apples to apples, internally consistent picture of the environment. And that'll be, again, that runs through all of our work. We want to be able to say, you know, what's soybean production globally this year? What are rates of urbanization across different continents and countries related to, let's say, economic growth? I'll start with our first map from the University of Maryland Department of Geography. 1994, this was published. This is a 1 degree by 1 degree spatial resolution map at the equator. That's about 111 kilometers on the side. You can almost draw it by hand. This is in the peer-reviewed literature. We're super proud of it. It was made from a simple a series of meteorological data that were greenness measures of the surface of the Earth, capturing the phenology. I'll zoom into a pixel in Arkansas, some mixed forest in Arkansas. And that was our first, kind of coarse resolution map. NASA produced the data inputs for this from the AVHR sensor, which again is a meteorological sensor. It's scientists at Maryland and NASA were trying to filter through the atmosphere and look at the land, and so they developed some methods for doing that and process some other data inputs. First at 8 kilometers, we see some differentiation of leaf morphology here in the forest. We got down to 1 kilometer with this same instrument. And then NASA launched this instrument called MODIS, or the spacecraft Terra, and on it was the MODIS sensor. MODIS had 7 land bands. So these were spectral bands that were designed to avoid the atmosphere. So water vapor, different things, talk about atmospheric windows. It goes down and gets reflectance from the surface of the Earth. So you had 7 of those bands specifically for land monitoring, and they were at 500 and 250 meters. So not the best map. We didn't make that map, but anyway, it's 250 meters, and we're getting down to a scale where we can see human action on the land surface. So that's cool. But this whole time, we have this other asset that's a US government asset. It's called Landsat. Who's heard of Landsat? Landsat's launched when? The first Landsat? 71. And Yeah, same deck, sorry. It was a 71 or 72, I might be wrong. It was a 78, early 70s. And they acquire some data over the globe, but after that they just do tasking, mainly for agriculture. In those days, we couldn't process the data digitally. How were the data served to the globe? Do you remember how people used the data? On glossy photo sheets. So the biggest photo processing lab in America was out in South Dakota where they had the receiving station. They'd send out tubes, and people unroll the image, put it on a light table, use GIS draw on it. So you've got this data depth, this really nice data. They're not using it. And even today, you go to Ministry of Forestry in Indonesia, heads up digitizing on images to map deforestation as a legacy of this lack of technology. We didn't have the algorithms or the compute to process these data. So we drew on these pictures. So that was one thing that was solved with, certainly cloud computing. We got better CPUs, we got better memory, all this kind of stuff, and pretty soon we start processing algorithms, machine learning algorithms directly on the data. Another limitation was that they didn't have a global acquisition strategy until 1999. So you have a very poor archive. But in 1999, moving forward, we have global acquisition. So we start thinking about the planet as a single target. The killer, though, was that you had to buy these data. To buy the archive would have been, $30, $40, $50 million. Nobody's going to do that. So you had to use the data you could afford in your grant, not the data you needed for any particular product. People used to get PhDs on one image. I got my master's degree on one image that I bought. Ridiculous. But in 2008, they opened up the archive. So we could then say, okay, from 1999 forward, we have global acquisitions. The data are now free, and we have cool compute. We can process these data. We have high performance computing, and we can do 30-meter maps. So it's kind of weird. Even though Landsat predates those other sensors, it wasn't until this confluence of these other factors came together that we were like, okay, we can map at scale with Landsat. So this is 30 meters. You can see the bottomland. This is the kind of forest you have around here, on the Tar River and the Roanoke River, these bottomland hardwood forests. And then up on top on the divides is this forestry dynamic. And so we can start building time series, and that's the amount of tree cover that turns over in like a decade or so. So you can start mapping very cleanly and discreetly the human activity on the land surface at 30 meters. So that's pretty neat. So that's where we are with Landsat. Just a little background on, just to help you understand if you're not familiar with the satellites. We have these polar orbiting, this is MODIS, polar orbiting satellites that are sun synchronous, so they're acquiring, in the case of MODIS, everyday imagery. The point being we have time series, so we can look at the same patch of ground with MODIS every day, with Landsat every 8 days. And with that really kind of time domain, that's where we see the dynamics of the crop phenology, the dynamics of deforestation. And so I just want to focus on, to stress the time domain, and we just kind of stack up these images. You'll notice here that there's a lot of clouds. We have a lot of QA. We process every pixel in the Landsat archive. We throw away the most of it because it's cloudy or hazy. It's just got some problem, or shadows. So on the front end, we're doing a lot of processing to kind of get our data in order. This is just a schematic. I'm just going to use this in reference when I show examples of data. You might be able to keep this in mind. So in this graph, the historic satellites that were daily but coarse resolution. So if it's covering the globe daily, it's broad swath, it's usually big pixels. It's too blurry to really track the things we're interested in. But these are the sensors that are coarse resolution, way out here, but daily. So they have a limitation of spatial resolution. We'd like to be here, which is daily high resolution. With Landsat, we have 2 right now. Landsat 9 is going to be launched early next year, maybe a year from now. We might have 3 up in space at the same time. They're offset by 8 days, so we have every 8-day acquisition. So daily, 8-day. The commercial sector, if they launch a single image, the kind of things you look on Google Earth, you're looking at a city, you see that sub-meter quality imagery, that is commercial, and its return interval for a single sensor is more than a month, maybe 2 months. Not great for monitoring a lot of things. But there are companies out there that are building constellations of these. And Planet's one of those. I'll show an example of that, where they have like 100 small sats, and they're doing 3-meter daily, which is crazy. And I'm not a fan of the commercial sector because I think our problems are so big that, and I don't think there's really a business model unless you get the government to pay for half the data. Anybody here work for Digital Globe or Planner? Digital Globe makes $600, $800 million a year from government, but they're a commercial venture, they're private industry. And the only reason that is the case is because in this spatial domain, below 10 meters is reserved for the commercial sector. Okay, so that's why that is where it is. We have some European satellites that are like Landsat, so we can have a virtual constellation of US government and European government stuff and come close down here to this 3-meter spatial resolution. This is 10, 20, 30 meters. But this sweet spot really is saved right now for the commercial domain. And I'm going to show some cool examples with it, but it's annoying because, again, if we're talking about climate change, big land use dynamics that are of importance to humankind and the environment, we're never going to be able to map at scale if we have to pay for the data. Okay, I just talked about this, high performance things, high performance computing, machine learning algorithm, consistent data, and progressive data policies where the imagery are free. And in fact, when USGS made those Landsat free, they did studies, and they keep doing these studies showing that the value added of their use pays for this system. All right, so they've proved that giving the data away is really a profit for society. Killing you guys with data, but I'll get to the applications in a second. This is the archive of Landsat, going way back to, this is for TM, doesn't go back to the 70s, but you can see how we get better and better and richer with better acquisitions, better combinations of sensors, and now we're getting about 250,000 usable images per year globally with Landsat. And we can start with something like this that's not corrected, it's just this mosaic of raw data that has different atmospheric effects, different seasonal effects in our pre-processing. And we have a data-intensive HPC. It's 15 petabytes. It's designed to read and write real fast. We can process the whole archive, come up with clean images that are radiometrically normalized, and an algorithm can be applied to this at scale, these type of data. And we can turn a time series of these data into maps of where are trees being cleared, where are trees regrowing. And so in this color scheme, the stable trees are green, red is lost, so that's the arc of deforestation. Blue is gain. We see a lot of blue in the post-Soviet Union when they abandoned collectivized farms and these forests grew back as secondary birch regrowth. This is IKEA from space because that's forest loss and gain co-located, the pink color. So wherever you see pinks, that's usually forestry of some kind. So our southeast, you know that around here. It's this southeast U.S., subtropical southeast U.S. is one of the most intensively used landscapes in terms of tree cover. About a third of it turns over every decade. And this is the trend in disturbance. So now this kind of is a kind of static depiction of dynamics, but here's the trend. So if we see the yellow early to red, you can see all these different things going on. Fire's very noisy. You have big or small fire years. But if you look at the tropics, oranges and reds dominate. That means they are ramping up since 2000, more and more tropical forests being lost. The signal that stands out here is this yellow one. And where's that? It's the Amazon. And why is it yellow? It's yellow because the peak of deforestation in Brazil was 2004, 30,000 square kilometers. And after that, the government, along with companies and civil society, worked together, a bunch of stakeholders. They put in a forestry code and they enforced it, and they slowed deforestation from 30,000 down to 4,000 square kilometers. The only example of that kind of intervention. You know, in the news from this last year, they had a lot of backsliding, and I'll get to that in a second. But that's the proof of the success of their policy. They were killing it through 2004, 2005, and they got down to a low around 2010. Now they're back up to around 10,000. And one of the tricks for environment is, you have to win every battle forever, right? That's the trick. You can't just get down to 4,000, 2,000 cents a problem solved. It's got to keep going. Okay, so that's kind of a simple introduction to the data and the sensors and an application at global scale. I'm going to go through how we do our analytical cycle, how we make maps, how we produce area estimates for different themes. I'll show you the themes, and I'll show some examples from different sources of data. But we have our feature space here. We work a lot on our feature space. That is the time series satellite data. We have training data. So this is supervised machine learning methods. We work very hard on labeling our calibration data to say this is soybean or not soybean, this is deforestation, not deforestation. We use decision tree algorithms, but we're playing around with the deep learning computer vision. We think this is, computer vision is intriguing because most of our stuff to date is just per pixel. But we're least interested in this. We think these two are the bigger things. Algorithm is third. We make a map, and then we have this iterative thing where the expert is interacting with the algorithm, usually adding more training data, but can also go back to the feature space, very rarely changing the algorithm itself. But at some point, there's a final map. And so that iterative process is like you make great progress your first 2 or 3 iterations, then there's a long tail where you're just killing yourself and trying to squeeze out this last best product. And in general, there is a point where like there's just not enough feature space for what you're trying to do. You don't make perfect maps. And the first big thing to know is that no map is right. I mean, maps are useful, but there's no map that is perfect. Maps are biased. The maps don't have statistical properties like uncertainty. So we're happy with this map, but that's not the thing that we can send to IPCC for reporting. We can't count the pixels of our map and say deforestation equals this. So it's very important. The next step is what do we do with the map to get to the area estimate, and I'll show that in a couple slides. But in terms of the map themes, this is a bit much, but we start with biophysical kind of vegetative attributes here that are very clearly identified with the satellite. So is it tall vegetation, short vegetation? Is it lacking vegetation? Is it dense trees or grass? We can map this at scale pretty easily. Then we get in the blues. These are more uses. We're differentiating natural land covers from uses, and this becomes very hard. The satellite has a harder time, and our algorithms have a harder time saying something's a pasture versus a grassland. That's like, forget it, very hard. So as we go from here to here, our mapping gets harder, but we can do sampling. We can sample at both scales, and with samples, we can interpret using photo interpretation methods all of these categories, and we can get our area of estimates that way. So we can try to map these, but we can also use sampling. So sampling is really important. That's what we use for our area estimations. So we take a map. It might be forest loss versus no forest loss, and we use that as a stratifier. Then we throw samples in those strata, and from those samples, where we collect reference data, we produce area estimates with known uncertainty. We use unbiased estimators. So we get an estimate of deforestation, for example, and then that area that comes out of it, we can go back and fix our map, and we can make an unbiased map in the end. It may not be perfectly spatially accurate, but this is the idea. So we map, sample, get our answer really here, and go back, fix the map. The samples. If you're a remote sensing student in geography, you always think of accuracies, but it's really about the areas. The areas are the thing that we get from the samples that are most useful for governments, for their policies, everything. If you tell a government that here's an 85% accurate map, they're like, thanks for that, that's wonderful. But you tell them, well, you got 10,000 square kilometers of deforestation, plus or minus 500 square kilometers. Oh, I get that. So the samples really are about area estimation. This is paper from Mark. Way back when, where we showed that that if we stratified based on satellite signals for mapping deforestation, we had huge efficiencies in terms of the number of samples we needed to look at to achieve a certain uncertainty. So if we look at is this the random up here? If we're a factor greater of 10 efficiency by doing targeted sampling guided by the satellite. So this is huge, a huge deal, and it just allows us to analyze things much more efficiently, much more definitively with the satellite as the targeting mechanism. Okay, so I'm going to start with the first application. This is a weird one. We have these at the top of that hierarchy, we map, let's say, lack of vegetation, tall vegetation, other vegetation in RGB here. So you see all the trees are in red, deserts are in blue. I'm going to talk about the bare ground, the desert category. So here it looks more like a desert. We map time series of this theme, and we're just trying to track where vegetation is lost over time. And maybe if you're interested in desertification, that's pretty cool, but generally people don't care about bare ground expansion. But bare ground expansion occurs, in North Carolina, huge last 30 years, with Raleigh, Durham, Chapel Hill, Charlotte growing. So when we look at the changes over time of this bare ground signal, I'll zoom into Dallas-Fort Worth, all of these blues are increased bare ground. And they're highways and the extension of a runway. They're commercial plots on interchanges. It's like the the airport's the new CBD, right? In Dulles, outside of Washington, the city grew to Dulles. There's more offices around Dulles than there are downtown DC. Same thing with Denver. The city's going to grow to its new airport. This is the signal we pick up in these time series of bare ground. What's weird is this bare ground expansion, it's really tied to economic development. So we can make a map of this bare ground gain and see that it tracks with Beijing growing, Shanghai. We see resource extraction signals. This is all China. You can see North Korea quiet. This is not night lights. This is bare ground gain from reflectance, surface reflectance, and you don't see much action there because the economy is static. Here's the US. I'm sorry you got the bright lights right on the screen there. But here you see fracking in Arkansas and around Dallas-Fort Worth. You see mountaintop removal mining. So these are all really highly extractive, highly intensive economic activities. So this is our map, and we take this map and we throw samples. And each sample, and this is a stratified sample guided by our map, and at each sample we go in and look at reference data. The reference data are time series of our imagery, but also Google Earth imagery commercial data where we can say, oh, this was a place that was a forest, it was an easement for a power line. Now it is a power substation. So we chalk that one up. That sample is being infrastructure, energy infrastructure. One might be an airport, one might be a residential area. And so from all of these samples, we get the areas of different economic sectors. And when we look at the aggregate story, we see really the global economic crisis. It just ramps up to around 2008, and then it just peters off. So you see in this very tiny signal, this is globally, our areas are not as much as Brazil deforests per year. Globally, you look at a needle in a haystack. But with these samples, we get pretty tight uncertainties because we know where to look. If you look at this by country, the two countries that dominate are China and the US. China, about a third of all this dynamic globally. China 7 times the infrastructure investment as the US. If you look at some of the other countries, look at Canada, Russia, Australia. You know why they would have big loss of vegetation? It's related to China. Yeah, it's mining and resource extraction. So Brazil sends iron to China, Australia sends coal, Russia sends oil. These red bars are telling you that resource extraction is a big deal in their economies, and that is also tied to this big bar here. So it's kind of cool. I mean, I like this. This student's going to graduate this spring, but it's you're looking at this very tiny area globally at a 30-meter spatial resolution, but getting some pretty interesting uncertainties by mapping a very simple theme, bare ground gain, and then using these probability-based samples of reference data to tell this much richer thematic story. Anybody have any questions on that? All right, so I'm going to go to the next one. Going down further into the hierarchy, I got a couple examples. We'll start with the general category, cropland. This is for Brazil, where we map the change dynamic. So where was cropland in 2000? Where is it now? And so we use the Landsat data to try and track this. Brazil is huge in expanding commodities, and most of those commodities are going where? Soybean goes to China for feedstock. And Europe. But China's a big deal. And so we have this gain map, and we throw the samples again. And when we look at the samples, we can say how much of cropland expansion occurred in the Amazon rainforest, how much occurred in the dry tropical Cerrado, how much occurred on land use that was already established, like pastures or other already established land uses. And we get these from the samples, great time series. And there are uncertainties in these graphs. You can see the uncertainties. So with our samples, because we know where we're looking, we have very tight uncertainties. And the bottom line is when you do this story, 80% of new crops is going on to pasture. And it's not a proximate driver of deforestation. They are intensifying everything. They are taking pasture out of production, but still getting more cattle produced by doing managed pasture where they're keeping it, they're doing cultivated pastures, they're doing semi-containment. They are super powerful at producing both beef and cereals and other grains. And you see this. In the Amazon, the clearing goes down. And that is that signal I showed you before that the natural rainforest peaks in loss in 2004, the policy takes hold, and there's very little expansion of cropland in the rainforest. That is, again, another proof of their success. And this, in particular, there's a soy moratorium where the big agro-industrials, Cargill, Bunge, ADM, they said, we're not going to buy soy on newly deforested land, and there's the signal. And they were true to that commitment. What we see also is that new cropland corresponds with profit. In this case, soybean profit. So, if there's money to be had, they're gonna add acreage. And a lot of times when they make their profit, they put it back into expanding crops because they don't know what else to do with it. The signal is widespread. It's across the whole country, but you have these new frontiers. We do field work. We just got back from field work in South America, but every time we do a new stratification using the map, we have a new frontier. So the latest new frontier is up here around a city called Paragominas. It's in the rainforest domain. They have to wait for the core rainy season to pass because they can't till it. And they can do one crop, but you have a bunch of new soybean up here. There's soybean up in Roraima. It's just an amazing dynamic. I want to show just one other slide on this story that shows the policy again. So here on this side, we have new cropland in trees in red for the first 5 years of the 2000s. So this is before the policy came in. Tree cover that is lost to cropland after that is all out in this other biome. So this idea, they call this leakage. Because you say we're not going to make new soybean fields in the rainforest, that doesn't mean the demand goes away. The demand is still there. They move out to the Cerrado and they expand. So that's a very clear effect of the policy success, but the spillover, the leakage of the policy. Okay, now we're going to go down the hierarchy to a particular crop. This is soybean itself, not just cropland. And it's just fun because if you're in satellite remote sensing, you've got all these phenologies to deal with between different crops. You've got different varieties of soybean, 90-day, 120-day. It's just a crazy signal to try and tie down. You've got it all the way across a continent with different planting dates. It's really hard. It's much harder than bare ground, I'll tell you that. So here, same idea. We make a map of soybean. In this case, we have to validate it in the field because we cannot tell soybean generically from an image in the growing season. So we create this population of sampling blocks, 20 kilometers on a side. We build thresholds in and we say where the high concentration of soy, medium, and low. We take samples within each of these strata, and then we have to go visit these. And in each of these blocks, we throw a second stage sample at a pixel scale, and we look at 20 samples within each block, and then we go to the field. And so this is what one of the blocks looks like. These are our samples that we have to visit. And we drive around and check them out. We check out the crop type, the condition, the stage, all that kind of stuff, record it. And then we also, in these yellow patches here, grab training data for mapping these blocks. And then we throw this at satellite data. So we map this block using time series of our Landsat and Sentinel-2 data. And we map the soybean. And this is a slide I really like because when we map the soybean at our sample scale, it shows that the high stratum really does behave as a homogeneous population. The medium stratum does behave as and it's not trained on this year's data. So we get this very clean, this is evidence of our sampling efficiency. And we can say we have 350,000 square kilometers of soybean plus or minus 6,000 for that year. Brazil doesn't have a statistical method for doing this. They call their cooperators on the phone. What do you got? What do you got? What do you got? They throw a number out. And this is tight from a statistical standpoint. And we do this in Argentina, Bolivia, Paraguay, Uruguay, the US. We just did it in China. And again, the idea of the satellite is, and the method, we can do apples to apples comparison of this commodity across different geographies consistently through time. And so we end up with a final map. And then we can track this dynamic. We can train our algorithm and track the dynamic through back in history and say where has soy expanded over time. You just see it expanded everywhere. It starts in these core areas and it just grows from there. It moves cattle out. Cattle move to more marginal lands, drier Chaco lands in Argentina, maybe wetlands. The pasture loses. Pasture gets pushed deeper into the Amazon, and pasture I'll come back to when we come to the fires, but all the cattle are moving farther away. from soybean, and we can also disaggregate it by biome and see which biomes are under greater threat. So again, this is what I just said. We can use this, do this method generically at scale and just track key commodities. We can do this for corn, we can do this for wheat, rice, and the like. Now I'm going to show you a commercial data example. This is fun, I think. This is for a smallholder landscape in Pakistan. So Pakistan has pretty good production of wheat, not as good in India, but they do a lot of intensive farming. They have inputs, fertilizer, and the like. But when we look at the field size, it's very small. So I'll show you, this is from Google Earth. I don't know what spatial resolution it is. It's one of our sample blocks. This is what Landsat looks like over this patch of ground. So Landsat's very blurry, and you can't do area estimation very well with this. I'll turn this into false color infrared. So now all the red is vegetation, and we're going to do winter wheat. So I'll show you what this looks like. So the point of this exercise is there are a lot of geographies, China, South Asia, most of the tropics, where field size is very small, and our pixels are too big. So in that schematic where we have high res, high temporal, the commercial data are really promising, very nice. And I'm going to sell product here for a commercial company. Here we have the Landsat data over the entire growing season for winter wheat in Pakistan. Just show you all of the acquisitions. There's 15 of them. And there's some good ones. You see the bright red, that's the wheat. You'll see that it turns rust colored as it senesces. Right there, it starts senescing. There it is, it's fully senesced. And so over 15 images, we can pile those up and make a map like this. But that's a very crude looking map. You can see it's blocky. It's too coarse to really pick up the data that well. This is the 3-meter data from Planet. I'm going to show you the time series they've collected. And just before showing, it's like 150 some images over 57 unique dates compared to 15. And it's at 3 meters. So this is all the Planet data for that same period. If you look at the dates, it's like every couple, 2, 3, 4 days. With these small sats. It's really cool. You see the phenology. At the end of February, it's peak. It's peak right now. And then it'll start senescing. Now you see the color changing. It's gone off peak. And there it is. That's crazy good data. The time series is amazing. It's got a little wiggle geometrically, but wow, that's awesome. So we can take these data, build a kind of composite time series. This is what the phenology of the crop looks like. We can go to the field like we always do. We do go to the field still. But we can turn this time series into a map that looks like that compared to that. So that's pretty sweet. I think that, yeah, amazing to me. So that's an input to area estimation. And so we did this in China. We did soybean in China, same idea. We build stacks of the 3-meter data, and now we can add China to the other countries for soybean. Now one of the environmental icons of our time is the rainforest, another domain. I'll show a couple stories about the 3 big rainforest areas left, the Amazon Basin, Congo Basin, and insular Southeast Asia. We use the same methods, and this is a big deal for climate change mitigation, right? There's a lot of initiatives with the IPCC, UNFCCC, certain bilateral countries like Norway. Norway, to make themselves, salve their conscience, puts a lot of money into slowing deforestation. And we can do the same work where we run samples, and we can see that Brazil's decline is dramatic, but the other countries, DRC and Indonesia, increase. We can throw samples on a regional basis and show that pasture is the big driver of deforestation in the interior Amazon. It's not soybean. Other things like fires are a big deal as well. And a lot of those ended up being converted into pasture. If we go back to this summer is really interesting. Who heard about the fires in Brazil? It's amazing. The big year for fire in Brazil was 2015, 2016. It was an El Nino. There were more fires in the Amazon basin that year than this past year, but it didn't get any traction with the press, the media. Nobody heard about it. I mean, way worse than this year. Why did we hear about it this year? Sorry? Could be climate summit. Anybody, who's the leader of Brazil? Bolsonaro, yeah. So you have this very right-wing leader who, when he's asked on TV, it's like, you were quoted as saying you don't believe the indigenous people should get 2 centimeters of land in the Amazon. He said, no, I said 1 centimeter. He's very hard guy. He wants to de-gazette national parks. He wants to put, so he is this big rhetorical deforester, rhetorically, right? So he's in power, and these fires happen. A lot of the fires were by ranchers to show solidarity with him. So they had a day of fire in this town called Novo Progreso, just to show, that they were off the leash and they could do what they wanted. So in the end, you had, and there's another couple factors, but you also had smoke in Sao Paulo. Smoke reached Sao Paulo, which is particularly noteworthy for the media, and people in Sao Paulo breathing the smoke. What's interesting is the kind of push, the political story that comes from that. I believe that Brazil's been sliding backwards for 5-6 years. I mean, I know. They have cut support for the indigenous reserve since 2013. Immediately, you see incursions, illegal logging, land grabbing. They have cut funding for their Embrapa Environment Agency to interdict and arrest illegal clearings. They don't go out in the field anymore. They've been put under the Department of Agriculture. So there's been a 5-year backsliding issue. But one of the interesting things about the stories were that the media says soy and pasture are the soy and cattle are the big causes of the fire. And Macron, the president of France, said we're not going to buy any more soybean if they're going to destroy the Amazon. Which is interesting because the soybean farmers aren't interested in fire at all. It's bad. They try to put organics in their soil. Any fire gets on their soil, it kills their soil, it becomes mineral. And so wherever you see, these are the active fires from this past summer. This is where the crops are. They're not co-located, right? The fires are inside the Amazon where the cattle are. And it's the ranchers who are doing the fires. That's where all the action is. And it's when Macron says that, all of the big crop producers, they go knocking on Bolsonaro's door. They're like, what are you doing, man? You're threatening our livelihood over these guys in the forest playing with fire. So it's really interesting. So that story was wrong, that it was soy, but I think it had a good political effect. Very strange thing. I think a lot of parts of the story were wrong in that these were not unprecedented. 2015, 2016 were worse. It is not anything to do with soy. But in fact, I think it's good because people's awareness is raised and it causes a lot of internal and rough dialogue inside Brazil. Just an example of some clearings in indigenous reserve. This is in Rondônia, where in 2013 FUNAI pulled out their guard post, and right after that the group of the Caripuna just started getting overrun by illegal squatters and loggers with guns. So that's a big side issue. In Indonesia, same story. Here are all our samples. We're tracking all the changes. And the crazy thing about Indonesia, it just blows my mind away. The biggest driver of deforestation in Indonesia, we can't attribute. It is land grabbing. So right now there's 9 million hectares of rainforest that's cleared and just sitting there. So people just bank it. It could be 8 to 10 years, 8 years on average before palm oil comes in. They don't have to deforest anymore. They don't have to deforest for like 10 years. They have enough land to expand. It tells you kind of how the mismatch is from, if you're an advocate for the rainforest and you have to deal with just clearing there's a lot of money to be made on the timber. These are the most valuable rainforests in terms of timber. That's why the clearing occurs. But then they don't let it come back. They're holding on to it. That's just an amazing result. It's one of my students working on this in Indonesia. We had bad fires there that year too. Now we go to the Congo. I just came back from the Congo 30 minutes ago or something, not too long ago. But this is the Congo Basin, the second biggest rainforest chunk, and the one we've worked in the longest for like 20 plus years. And which country here is like the big story? You guys know your Central African geography? This country here, Democratic Republic of the Congo. Look at all the forest clearing there. Look at Republic of the Congo, very quiet. Gabon, very quiet. There's huge demographic pressure in DRC. This city, Kinshasa, their capital, has more people than these 3 countries combined. So this is the big threat to the rainforest. These countries, logging's the threat, but here it's really the almost 100 million people feeding themselves. I'll show you an example. There's the loss. We do the same thing. I just come back to our method. It's generic. And when we look at the samples across the basin, we can say how much of it is primary rainforest, how much of it is secondary re-clearing, and it's about half and half in the Democratic Republic of Congo. More primary forest is disturbed in these countries because it's logging. They want to get the nice logs out of the pristine forest, but it's not deforestation. It's not full clearing. This is the killer. This is amazing. So here are the land use outcomes from clearing in these countries. If you're on the coast, you see these blue dots. That's palm oil. So bringing in some big agro-industrial scale clearing. If you get in the interior of Gabon, Republic of Congo, Cameroon, it's logging. And then you trip over to DRC, and it's 92% smallholder ag. So here's the deal. Here's the demographic deal in Democratic Republic of Congo. We've got let's say 80, 90 million people right now. It's going to be 200 million by 2050, 380 million by 2100 per the UN. It'll be the 5th most populous country in the world per UN projections. In this picture, there's no country, there's no state there. There's no food aid going in, there's no oil being exported for cheap imports. This is what that's basically smallholders feeding themselves. And the old dictator of the country, Mobutu Sese Seko, had a constitution that had 14 articles. They're very high aspiring, principles of the country and rule of law and all that. And they used to joke about the 15th article, Article 15, which was débrouillez-vous, which means you're on your own. And this is that from space. This is 100 million people almost feeding themselves. And the amount of clearing done by axes is half of what Indonesia does with machines. So this is just, I can't overstate how amazing that is. And when you extrapolate our estimated primary forest clearing with the population projections, the forest is gone by 2100. And we have the trends and all that kind of stuff. On the other side, we have the Republic of Congo, which is the quieter, more organized Congo. It has 4.5 million people compared to 90 or so. And their big issue is logging. And so when they want to report to the IPCC, they need to track what they call degradation. Degradation is not deforestation. It's just the removal of biomass without clearing the forest. This is their job. It's a very hard job. But I'm going to show you again the commercial data's advantage over the public data, the public data being Landsat. Landsat acquisitions are very sparse. This is a logging road coming into an intact primary forest. In these forests, there are elephants, forest elephants, chimpanzees, gorillas. Here's the logging road. This is the best image for seeing the extractions. You can see some of the extractions here. Then check this out. After that, the next best image, you see nothing of the extractions. It's all recovered. The green vegetation just fills up the voids, and all you have left are some logging roads. And that's what our map shows. Our map only shows the roads. It's a problem. It's not great. Here's what this 3-meter near daily data shows. And I just select a few from here. I don't show the whole time series. But here's a reference image. Here comes the road. Here's the logging. Now you see some better extractions of the skidder trails. Look at that image. That's a huge footprint. That's a lot of biomass. When you see the logs line up on the roads, it's a lot. And then it's gone. So the time series and the 3-meter resolution of this commercial data are fantastic. It's unbelievable. So in the end, all you have left is the logging roads. You don't see, in this optical data, you don't see the thing. This is our map. That's what we're missing. So that's kind of cool. For this country, for these kind of countries, they have this certain class of countries called high forest, low deforestation countries, Republic of Congo, Gabon, Guyana, Suriname. This is the kind of data we need to use to map their stuff. And so we do field work here with the same idea, 2-stage sampling. We go out with a LiDAR and we try to track in a probability-based way the area and the change in structure or carbon stock of this logging effort. Not to explain all that, but it's following the same path as we do with soybean going to the field. So I'll just show you, just in the end, just one summary. slide for DRC where our capability is really just limited by the imagination. What land dynamic is important for what biogeophysical process? We can map surface water inundation. We can map settlements and the like. And this example is a mapping of settlements. We talked about, I said there's like 100 million people in the Democratic Republic of Congo, and we can map those people the same way. There are health survey data where we can take the samples and put in the number of people in the houses that we see in the samples, and then come up with an estimate of the population of DRC. And then we can add all this stuff up. So we can start with water, tree cover, primary forest, intact forest landscapes is another layer, which is like the best core blocks of rainforest. Wetlands, so which of the forests are wetland formations, which of the savannas are wetland formations. Where are we losing tree cover? Where are people living? Where are they doing agriculture? This is what they call the rural complex. It's shifting cultivation. And where, let's say, GIS layers of interest like protected areas. And that's kind of where we want to go with the globe. We want to have these key kind of land cover, land use dynamics mapped and tracked over time so we can see what's happening to the planet. We do it for some themes individually, but this is like going towards a unified field theory of this approach. The last thing I show is this idea of putting Voronoi polygons around the settlements and just showing where population density is in relation to these last blocks of forest. And so this is where the conservation potential is. This is where the last of the best is. And if you do our work, it's where the government should probably put no-go lines, right? No-go zones. If you want to limit your emissions, if you want to get the co-benefits of climate mitigation through biodiversity conservation, just don't go to these places. Buffer out the protected areas, et cetera. And this is a little snippet, more high resolution with these layers adding up. And you see the human footprint just really dense and getting light as you go out to the rainforest. So that's it. It's just about, can we, of all the land changes that we mapped in the last 30 some years, 40% are human, directly attributable to human land use. There is a big climate signal, tree cover gain in the high latitudes. The tundra is getting woodier, montane forest, montane woodiness is increasing. But still, the dominant signal on the planet is direct human action and land use. And so we want to track that. My basic take-home message is that right now, with our data, we are in the best period of doing this kind of work. We have more data than we ever had. We need geographic domain experts with quantitative skills to exploit all of these data and tools. When we do both mapping and sampling for area estimation, we can make products that are directly informed decision support systems like policies of national or international protocols. So that's the huge deal, to be very relevant to society, societal benefits, and that it's kind of open season to be really creative with these data because we have just tons of it, and it's just you have to have the imagination to ask an interesting problem, find the problem, ask it, and solve it. So that's it. That's all I got. Thanks.
Are there time for a couple of questions? Are there some questions for Dr. Hansen?
Please.
Have you done the same thing for water?
Yeah, I think I have a few extra slides there for water, maybe. Water, we do interannual and we do monthly water, and we can characterize intraannual seasonality of water. So, for example, this is the Baratsi floodplain of Zambia. It fills up with water every April and May. But we can also do interannual. This is Lake Urmia in Iran. All of the Central Asian lakes that are being used for irrigating crops like cotton and stuff and building reservoirs for cities are drying up. It's like the RLC problem. So yeah, we do every pixel. You can see the reservoir here is new, it's recent, and then the lake shrinks. So we have in our database every pixel for 20 years mapped as water or not water.
Brazil is the major producer of pulp, eucalyptus, that is
Right.
used for tissue.
Yep.
And they are planting a lot.
Yes.
Sent to China and other places.
Right.
Have you seen
For sure, for sure.
And that, and the follow-up question is, are there deforesting and planting eucalyptus? Can you see that from your data?
Okay, most of the eucalyptus is going on to already deforested lands, except for maybe some parts of South Brazil, like Paraná, Southeast Paraná. But the country with the biggest gain in tree cover in our time series is Uruguay, and it's just taking pampas, taking the grassland that's usually historically range, and putting eucalypts. And as you go up into Brazil, the whole southeast is eucalypts, but it's not deforestation. It's very old, like pasture, except for maybe that.
It's a land use change.
Yeah, it's a change from one land use to another.
Yeah, but we cannot say that they are removing the natural forest.
No, not. They are, but not. It's not the dominant thing for the forestry.
Follow-up question. In Canada and northern United States, there's another fiber, pine, that's used again for tissue and other papers.
Right.
And there have been some advertising by some of the Greenpeace group, like we are flushing our trees in the toilet. Have you seen a decrease in the?
Well, it's interesting. I mean, I'll characterize Canada's interesting because when Canada reports to the FAO their area of forest, it never changes. That's because FAO allows you to have a land use criteria when you say something is forest or not. So they have a big polygon over like the middle of their country, and that's their forestry land use. They don't have to be trees there. They could clear cut it. It's still forestry. From their perspective, they're not going to put a Walmart there. It's going to come back as forest. It'll be a century. So they have this, they have this kind of greenwashing of their data, in my opinion. So I think, particularly the North America, with climate change, you have some mortality due to droughts and heat. You have the mountain pine bark beetle, which is salvage cut, widespread across British Columbia and even down into South Dakota. And then you have logging. I mean, I think this place is a net source big time for carbon. And it's not going to recover anytime soon because the cycles are so long. And they get a free ride, because if you took all the deforestation in Brazil and stopped today, you'd have forest in 20 years. But you clear cut all that old growth in Canada, it's not coming back for a century, but they call it sustainable. And even in Obama had an energy plan, a clean energy plan. I think it went nowhere, but the foresters fought really hard to say that when you cut down forest, that was the equivalent, and used it for wood pellets, that was the equivalent of wind or sun, because there was this implicit thing that 80 years it'll be back, sure. So I think the higher latitudes get a little bit of a free ride on their kind of sustainability side of these forests. I don't know if that answers your question. I mean, I don't know where my toilet paper comes from, but I will say traceability is a big deal. Commodity chains and knowing where these things are coming from. When you go into Whole Foods and they have like Earth Balance spread, and the first ingredient is palm oil. I'm like, what do you feel good? We need to know where these things are coming from if they're sourced, and I think that's doable. I don't know who wants to do it. The governments don't seem to really want to do it, but the pressure we could apply will work on traders. The traders respond to that if we act more in a grassroots way. But the toilet paper one's new to me. I don't know anything about that. Mm-hmm.
Yes, could you comment on the value of the Google Earth Engine in doing some of this type of research?
Well, Google Earth Engine is, to date, for academic institutions and other nonprofits, free platform to access the Landsat archive and process algorithms of map. And it has democratized in a large way mapping at scale. So it's a fantastic tool. Our first run of our global forest product was done not on Google Earth Engine, it was done with the team, run offline. But we collaborate with them. We still run our alerts on it, so we collaborate with them, and it is very powerful. For us, we have our own system and our own interface, and we've never left that. And we're just lucky, fortunate enough to have a big enough capacity to do it ourselves. But for everybody else just getting into it, you go there and you get used to it, and it's a great asset. The question is, I mean, they do have a profit model. If you're a company, you're going to pay 5 figures a month or something to use it. And as long as they can, I think, make money that way, they can support the free side of it. but it's also, you could build your whole infrastructure, your whole coding base around that, and one day it becomes commercial and you're done. I don't know, so this is the risky thing for me. But they're fantastic. We know the whole team, and they're super smart, and they're responsive to putting on, new tools and executables that people think would help. And so I think Google Earth Engine is just is a great thing for the community. Mm-hmm.
When you're training your data, such as with the soybeans,
Yeah.
if you're measuring a different crop, do you have to do each crop? Do you have to train each crop individually?
For sure. I mean, when you're doing training data, the number one thing is to know what is most likely to be confused with the thing you're interested in, right? So like soybeans is dry beans. The plants are almost identical. There's a little tendril, whatever. It's just, it's really hard. So, even water you think is intuitively simple, but, dark spruce forest on a wetland, it's a forest, but it looks like water. The downtown, midtown Manhattan looks like a lake, actually, with all the light extinction of the skyscrapers. It's just strange, right? So it's really important to know all that variation, and you got to train on all of it. You got to know all of the crop diversity. Our most crop diverse state is North Dakota, and we got to train a lot on North Dakota. Iowa, it's corn, soybean, maybe some alfalfa. It's the easiest place to map in the world. So yeah, you got to work. This is the environmental knowledge. Like, you have to know what's out there and where, and chase it. Yeah, good question.
Next question. When you're looking at it, have you looked at other places to find signals to do the comparative analysis and statistics? Like you could have a different type of satellite that would pull up a different frequency or wavelength or something like that.
Yeah, there are radar satellites and stuff. We have a little box around the globally acquired, freely available data, and that eliminates a lot of the researchy kind of instruments because we couldn't use them at scale. There is one radar instrument now that is European, and it's working in the way we would approve of, and we're testing that, and we haven't found a real compelling need to integrate it. But yeah, always, I think always one of the tensions is we always throw up some new researchy thing. We're not good at the boring same thing. Weather we are, but for land we're not. But that's our space. Our space is the boring operational signal that we can build a time series off of. Thanks.